All right. So we had done this one. So now let's go to letter B. We'll do one or two more of these. I want to make sure we do the problems that I did skip yesterday. But look at this one now, and then understand why this one actually adds another layer of some difficulty to this. Because if we're going to try to undo this, this is always our x squared. I don't want that to be blue. But it's not just an x squared, it's a 4x squared. So over here in this first one that we did, this was an x squared, but we had a 7 in front of it. The nice thing about this, all of our talk of prime numbers yesterday, 7's a prime number. So the only way I could have gotten that is with a 7x on one of the sides and the 1x on the other side. Your issue with 4 now is, don't you have multiple options to get a 4? So the issue with these now start to become, this could, and honestly, I don't know. A lot of times when I start these, I wouldn't necessarily know right off the top of my head. 2x and 2x would give us a 4x squared. But wouldn't a 4x and a 1x also give us 4x squared? So there's now a decision to be made. And that's why right now it's kind of like a little puzzle. When we go to 27, we know that has to be a 27. And again, let me get rid of the 4x and the 1x. I don't necessarily know that that's what it is. And what we know is these guys here better add up to be this middle number. So take a minute. I really want you to kind of contemplate this, because this is really what these problems require you to do, is think of some different combinations in order to make this work. So take a second and figure out what could we have, in these spots at the top and then the two spots on the side, to see if we can come up with a combination that would satisfy those three conditions, that we get a 4x squared, we get a 27, and then these boxes here better add up to be the negative 39. Okay. And to be perfectly honest, I got to figure it out myself real quick. Anybody got it, Ahmed? What do you think, Ahmed? So right here, you're going to put a 3? Okay. 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 You mean right here? Okay. Okay. So, all right. So let's test this real quick. So what we have to make sure of, does the 4x multiply by a 1 and give us this square here, this rectangle there? Okay. Yeah. All right. So that's good. Then we would check, does the 9 multiplied by the 3 give us the 27 that we know we're supposed to get? Yeah. So far, so good. If we then multiply to get these individual boxes, the 9 and the 4 would make a 36x. The 3, okay, so we'll get to, that's good. what he's now saying, because that would give us a 3x. So if I now added these up like I'm supposed to, really, really close, right? Because this adds up to be 39x's. We wanted this to be a negative 39x. So all we need to do to make sure that they add up to be negative is if we make both of these negative 3 and negative 9, isn't a negative 9 and a negative 3 still going to give me this 27? Yeah. But now we get a negative 3x and a negative 36x. We can add those up. That's going to give me that negative 39. Okay? So definitely takes a little thinking in terms of being able to come up with this. All right. I only want to do one more because I'm not going to give you a ton of these right now. This is not the main focus of our chapter, but just again to make us think a little bit, understand these area models and how we're undoing this. So let's do one more. Let's go to number 6. I would strongly recommend with these drawing your boxes. So let's try one more. We know this has to be a 5x squared. So whatever you put right here and right here, better multiply to give you 5x squared. And we know this down here better be 8. So let me do a different color there. Yellow. So then these two spots better multiply to give you the positive 8. This one should be a little bit nicer. So we'll see if we can get this one. You get it? Nice. You have to remind me again. Do you go by full Andrew? Yeah. Okay. All right, we're gonna go with Andrew because he's here. He says he's got it. I haven't looked, so I'm gonna trust him. All right, what do you got for this spot right here, Andrew? 5x. And what'd you put up here? Good. So the reason this one should be a little bit nicer, that's the only way you can get a 5x squared is with a 5x and a 1x. So there's not a lot of guessing there. There is no guessing at all. Those have to be a 5x and a 1x. Where we now have a little bit of a guessing game is the 8 could have been a 1 and an 8 or a 2 and a 4. Also the order, where you put your 2 and where you put your 4 could also change things a little bit. So what'd you put up at the top, Andrew, with this? A 4? And what'd you put at the bottom? All right, so he said he's going to put his 2 here, the 4 up there. Those definitely multiply to give us the 8. So now let's test the individual boxes. This is 2x. This would be 20x. If we then add these two guys up, does that give us the middle term that we're supposed to be getting? Yeah. Okay. Now, I didn't do it in the last one, so I should probably do that. Go back and do that. But now we write these out as their individual factors. So one of our factors is this 5x getting increased by 2. And the other factor is the x getting increased by 4. So if we were to take this and multiply this out, it would give us the original problem that we started with. Okay. So on that previous one, if we go back to this one, because this is really ultimately what we want, I never actually wrote it, we would have a 4x minus a 3 multiplied by this x decreased by 9. That's what those factors would look like to multiply and give us this trinomial. Okay. So some tricky stuff there. Makes us think a little bit, hopefully understand how all these are playing out. Okay. All right, now, I do want to go backwards. I do want to get to some other things. The other stuff here is a little bit easier, so let's do these real quick. So if we go back to the previous page, so now go back to the previous page that we skipped. Still factoring, but a little different kind than what we've been doing in the last 2 days. If I have you multiply this out, first let's talk about this real quick though. Notice the little pattern here, just so we can make this easy. See how the first term and the last term are the same? They're both x's. At the same time, both of those constants are 5s. The only difference, so we have an x and an x, we have a 5 and a 5. The only difference is one is a sum, one is a difference. If we go to the next problem, notice that same pattern. 3 and 3, so the second numbers are the same. And at the same time, those first terms are the same, 2x and a 2x. Same with letter C. The first terms are the same, x and an x. And then the last terms are also the same. They are both 9s. But again, the difference, only difference, is one's a plus, one's a minus in all of these. So that's a pattern you want to recognize. First terms are the same, last terms are the same, one's positive, one's negative. So then let's see how this plays out. If we actually go through and multiply, x times x would give us x squared. The x times a negative 5 would give us a negative 5x. It's the 5's turn then to get distributed. So 5 times x is 5x. The 5 times a negative 5 is a negative 25. When we now go to combine like terms, we're going to get our x squared. But look at these like terms here. If I take a negative 5x and I add a positive 5x, isn't a negative 5 plus a positive 5 0? So those middle terms are going to drop out, and all I end up with then is this negative 25. Okay? So the middle term's dropping out. Keep your eye on that. Next one's 2x times 2x is a 4x squared. 2x times 3 is a 6x. Then take your negative 3 and distribute it. Negative 6x. And then the negative 3 and a positive 3 is a negative 9. If we then look at these middle terms, a positive 6x and a negative 6x should also cancel each other out, leaving us with just a 4x squared minus a 9. So hopefully, we're all bright people on my screen right now. We would anticipate something very, very similar happening in letter C, right? So if we did this, x times x is x squared. X times a negative 9 is a negative 9x. Take your 9 and distribute. So 9x and then a negative 81. These cancel, and we just get 81. So recognize now what's happening. So let me get rid of all the work over here so we can focus in on how we could do this a little quicker or undo this when that time comes. If we recognize this pattern, aren't we really just taking this x and squaring it to get the first term? And are we really just taking this 5, squaring it to get that last term? There is no middle term. So if I took 2x and I square it, doesn't that give me 4x squared? And if I take the last term of 3 and square it, doesn't that give me my 9? There is no middle term. The x multiplied by this x is our x squared. The 9's multiplied together give us our negative 81. There is no middle term. So real quick, before we go down and undo this, without doing this work, tell me what you think this would equal. So just write this at the top. Without having to do all distributing, we should go right to this answer very quickly. The other thing I should also point out, notice how they all end up with a minus sign when we go to do this little problem at the top of the page. What do you think, Cam? Good. We all agree with that? All right, so if we notice that pattern, that's how we can do this. So now the question is, what this is called, so I'm actually going to come down here, and I'm going to have you fill in this here. What the pattern is called that we're currently working on is what is called a difference. So at some point when you would have been learning sums, differences, quotients, products in your math lives, difference meant subtraction. If you have a difference of numbers, it's subtraction, and it is the difference of 2 squares. We could even put perfect squares in there, but it doesn't necessarily have to be a perfect square. So here's what this now refers to. So now let's go back to this and work backwards, because this is now ultimately what we're doing. We've been multiplying for a while. let's say I now start you with this problem. Do we agree that this is a difference that we're subtracting, and that this is a perfect square of x, this is a perfect square of 5? If you recognize that, this is how this has to play out. Whatever we squared to get those, with one of them being positive and one of them being negative. So if we look at this next one, notice how this is a difference. This is a perfect square of 2x. This is a perfect square of 3. Notice how we get a 2x minus 3 and a 2x plus 3. This is a perfect square of x. This is a perfect square of 9. Notice how we get x plus a 9, x minus a 9. So let's go to one with numbers right away. Let's say I go to this one, and I want you to factor that. If you recognize that this is a difference that we are subtracting, two nice perfect squares of x squared and 49, what those are squares of, this is a square of x, this is a square of 7. What this has to give us is an x and a 7 added together and an x and a 7 subtracted from each other. We can jump right to that very quickly. All right, does that make sense? Before we do another one of these, let me give you an E. That's another nice one before we start adding a different layer to this. Try letter E. So add that in there. X squared minus 25, and tell me what you think that would factor into. Oh, yeah. Nice call. Yeah, you better get it right. Yeah, so Ms. Kubowitz just pointed out this is letter A, right, at the top. So the x has to be the first term. We squared to get to 25 is a 5 and a 5. One has to be a plus, one has to be a minus. Okay, so C is the next one that I want to go with. 81 is a perfect square of 9. X squared is a perfect square of x. And if we go to the other term is the 4, that's a perfect square of 2. As long as it is a difference, which it is, it's a minus sign, then we just take whatever we squared, so the 9x and the 2, and we know this has to be a 9x minus a 2 and a 9x plus a 2. First term are the same, last terms are the same. One's a sum, one's a difference. All right, try letter A. It's a difference. Those are both perfect squares. Now that we don't have numbers, just tell me what you think A would be. Okay, anybody got that? What do you think? All right, yeah, Cam, go. It is just A minus B and then A plus B. All right, one more before we add the final little layer to this. Just do one more nice one, hopefully. X squared minus 100. Just show me that you know how to do that simple guy like that. All right, hopefully we got it. Again, what we're looking for in the future, it has to be a difference. We have that. We're subtracting. We can only have two terms, and we only have two terms. Both of those terms must be nice perfect squares, and these are. So this hopefully then is x minus 10, x plus 10. It doesn't matter if you put the plus first or the minus first. As long as one is positive, one is negative, you're good. Okay? So now, letter D, the one I've been kind of avoiding here. Not that it's terribly, terribly difficult. But here's what we now want to look at in letter D. Understand our definition for this shortcut. It has to be a difference. This is a difference. So we satisfy that. It has to be two terms. We satisfy that. There's two terms. But they also need to be nice perfect squares. Is there anything I can square to get a 72? A nice number to square to get 72. No, even 2, you can't really square anything nice to get a 2. However, so this is not a difference of squares, at least not yet. Remember how we started yesterday? Remember how we talked about a GCF? Isn't there a greatest common factor between 2 and 72? Yeah, 2, right? So what we need to do is pull this 2 out. Well, let me not put that just yet. So I'm going to pull the 2 out. What that would leave me with is just the x squared for the first term minus, and then what's left over for the 72 would have had to have been a 36. After pulling out the greatest common factor of 2, now let's look and see if we satisfy our definition. Is what is left over a difference of 2 terms, and both of those terms are nice, perfect squares? So remember yesterday we had some where we pulled out a greatest common factor and then we still had to continue on with that extra step. That's what's going to happen here. So we now need to factor this to be x minus 6, x plus 6, and then that 2 needs to come down with it. All right. So the GCF, you're always going to kind of look for that guy first. And if you have one, pull it out, and then we go through with what we've been doing these last few days, either a difference of squares or the trinomials with the little area model. Okay. All right, so now what I want you to do, so if you go to, you don't necessarily have to go there, but your homework is out of the Ready, Set, Go packet. It's going to be page 30. I want you to do 1 through, these are old problems that we just quizzed on, graphing either in vertex form or not. And then these are now our factoring problems. I want you to do 1 through 16. That, since I have 1 minute to burn before the weekend, pay attention to these directions. Notice how some of these are 2 terms. So this is a nice difference of perfect squares. We just did this one. If we start having 3 terms, then it's the whole thing that we spent a couple of days on. Multiply to be a negative 24, but add up to be the negative 5. Also, look at your directions here. If you have a common factor first, you need to pull that thing out. So our first step in all of these is to look for a greatest common factor. And if there is one of those, we want to pull those out. Okay? All right. See how that goes. We're going to basically, the next section is kind of a review section. We'll spend some time on these again on Monday. Just plan on the test probably Thursday and or Friday of next week. Okay? All right. We'll see you guys. Have a good weekend. Thank you, too.